Hello once again, and let's get into the final round of given forms and identities that we could just use and exploit as best as we can. Right? At no point am I ever going to ask you to prove the double angle formulas or the half angle formulas. At no point am I going to say, prove this thing that you have on your formula sheet. The job you have is to use those to prove new identities, to prove new formulas, to make appropriate substitutions. And that's going to be job enough. So let me give you just one more set. We won't even really get into the proof, the derivations of these, but I'll give them to you all the same. And then we will start using them however we see fit. So the identities in question that we're going to have to round out the total formula sheet basically is the sum to product and the product to sum identities. And the way you get at them is by using the sum and difference formulas for sine and cosine at the same time. So it's going to work out that if you did sine of u plus v, where u and v are any two angles or numbers or variables, and add that to sine of u minus v, you end up with 2 sine u cosine v. And after a little bit of manipulation, you end up with the product of sine to cosine of different numbers is a half of the sum of each of those. So we go from a product to a sum. And we can do that again for sine of u plus v minus sine of u plus v, or minus sine of u minus v, sorry. We can do that for cosines. And so these together gives us 4 new formulas. And they're rather cumbersome. But there is another way of writing these. Instead of doing that, solving for the product based on a sum, we end up with these much nicer forms. We kind of do some substitutions here. We substitute u to be that awkward thing and v to be that awkward thing. But we actually end up with, if you're adding sine of 30 degrees plus sine of 45 degrees, say, then you can find that exactly, and it's not sine of 30 plus 45, but rather it follows this formula. And if you want to take the time, you can derive these forms from these equations we had in the previous slides, making these substitutions. They follow directly out of that, which is kind of nice, kind of neat. And they're just exactly that, actually. I'm not trying to oversell you on them. They are kind of nice, and they are kind of neat. They are very situational in nature. But at the same time, if you can recognize that you can use them, odds are pretty good that using them will make your life a lot better, a lot simpler. So if you have some awkward form such as this right here, if you recognize that you can use the sum identity for that, hey, life got a lot better. Working with this guy is a lot easier than working with that. But that's me anyway. Let me show you what I mean. Let's say I wanted to find the exact value of cosine of 255 degrees minus cosine of 195 degrees. Well, we can do that without using the formulas we've just got introduced to. Right, cosine of 225, that's 210 plus 45 degrees. 195 is 150 degrees plus 45 degrees. I could use these sum formulas twice, and then I could take that difference, and that would give me the same thing that I would have gotten had I just recognized, oh yeah, this is a difference. I can turn that into a product. And using the appropriate formula, I end up with the same thing I would have gotten, but with much, much more work, to be root 2 over 2. Which is kind of fun, kind of neat. But again, right, at the same time, that's all it is. Kind of fun, kind of neat, kind of useful. Never ever truly necessary, probably. Unless you're into a very, very contrived set of circumstances. Generally not really ever that super awesome. So hey, let's get into something contrived. Right, recognizing that you could work around this, albeit with a little more time, let me give you something that you technically could still work around, but you really, really don't want to. And I'll give a little clarification here in a second. Let's say I wanted to prove the identity that sine x plus sine 3x plus sine 5x over cosine x plus cosine 3x plus cosine 5x is equal to tangent of 3x. Oh boy. We have double angle formulas and we have half angle formulas. We don't have triple angle formulas. We could derive them because 3x is x plus 2x. We do the sum formula there. We do the double angle formula for the 2x. We could derive a 3x. And arguably, we could derive 5x. But that would be so impossibly messy that we'd have no hope of reasonably getting through that and keeping up with everything, keeping everything straight, and miracling out some manner of factorization that would make everything on this side reduce to tangent of 3x. So under these very contrived set of circumstances, the real viable option, and in this case, yeah, maybe just one, is recognizing, okay, I've got sine of 3x over cosine of 3x. That alone is tangent of 3x. So maybe let's just put up a Hail Mary play. Let's hope that if we combine the sine x and the sine of 5x, that will just vanish, and the cosine of 3x, I'm sorry, the cosine of x, cosine of 5x, that will just magically disappear, leaving us just with the sine of 3x over cosine of 3x. Well, let's give it a try. Right, I've got sine x, sine 5x, that's being added together. So with a little bit of manipulation via the sum to product formula, I can write that as 2 sine 3x cosine of negative 2x. And cosine of negative 2x, of course, is the same as cosine of positive 2x. Cosine is even. We do the same for the cosines. We get cosine 3x cosine 2x all times 2. And we make the appropriate substitution here. Oh yeah, it's that pretty. The cosine of x and the cosine of 5x combine accordingly. The sine of x and the sine 5x combine accordingly. We have a greatest common factor in the numerator, sine 3x, that gets factored out. The greatest common factor in the denominator, cosine 3x, gets factored out. The remaining factors cancel, leaving us with sine 3x over cosine 3x. That's our tangent. Oh boy. So how do we feel about that? It's a little much. That's a little much. And I'm going to go ahead and say that under any timed circumstances, you're not going to have to deal with something as esoteric as what we're looking at here. This feels very harshly academic in nature, and harshly indeed. So, recognizing then that we're not going to ever have to, with the clock ticking on us, find the proof of this, do we at least appreciate what happened here? Right? Do we at least appreciate that with this example, the cosine of 255 degrees minus cosine of 195, that the identities we had in place can help us circumnavigate rough waters, arduous waters, tedious waters? And do we also recognize that, well, when things get really hairy, and maybe they're the only game in town, that we can at least suss out what happened if we can't do it ourselves? So degree of difficulty wise, I'm never going to give you an identity like this and say, okay, in the next 55 minutes, give me a proof. That's not going to happen. But can you at least, if given the steps I have laid out here, can you trace that down all the way to the end? Or conversely, if I gave you these steps where maybe a mistake was halfway through, could you, I'll play that game, could you identify where the mistake happened? That's really what I want us to be able to do with these identities. Either recognize that they can be a clever substitution to clean up matters quickly for us, or recognize that they can just be used as a general proof technique that other people use. And I think that's enough for now. I think that's a big enough ask. Because again, we've got all these formulas and all these identities at our disposal. It's really going to be enough just to keep them all straight in our head and to recognize when we can do what with them. So that's it. That's the plan. That's my expectation of you. That's my ask of you. So we're going to take a little more time in class to make sure we can do that. Let me know what you're struggling with, and then in the next set of videos, we will start looking at equations that are not always true. Don't play Here's the Storm. It's a bad game. So let's do that, and you guys have a good one.